This is Precalculus, lesson 11.2, exponential functions. So we're at 11.2, exponential functions. So what we're dealing with here is functions of this form. F of x equals b to the x in some shape or form. B, where b is a positive real number. B needs to be positive because weird stuff starts to happen if we have something like, if you had something like f of x equals negative 4 to the x. Well, as you get, first of all, if x is integers, you're constantly swapping back and forth between positive and negative y values. And if x is non-integer, just a lot of weird stuff happens. So we're just dealing with b is a positive real number. And we might be adding stuff, we might be subtracting stuff to tacked onto this. We might be adding and subtracting stuff here, but in its base form, no pun intended, we have some positive real number to the power of x. So the gist of an exponential function, x is in the exponent. X is part of the exponent. The gist of graphs, we could say if b is greater than 1, then the overall shape we get is like this. It really should go steeper and steeper and steeper as you go. So we have exponential growth, okay, where label x-axis, y-axis, arrowheads. So this would be like, so it might be something like f of x equals 2 to the x. Okay? Well, table of values wise, we can see if x is x, y, if x is 0, 2 to the 0th is 1. So this is going to go have a y-intercept right there at 1. If x is 1, 2 to the first is 2. If x is 2, 2 squared is 4. If x is 3, 2 cubed is 8. So we're just getting bigger and bigger and bigger like that. But how if we're rewinding to negative numbers? So if x is negative 1, 2 to the negative first, the same thing as 1 over 2 to the positive first, which that gives us 1/2. If x is negative 2, x to the 2 to the negative 2, same thing as 1 over 2 to the positive 2, that gives us 1/4. If x is negative 3, 2 to the negative third, same thing as 1 over 2 to the positive third, that gives us 1/8. So we have reciprocals going here. 1, 2, 4, 8. I didn't repeat, so 2, 4, 8, 1/2, 1/4, 1/8. What's happening is it's getting closer and closer and closer and closer to 0, but there's no value of x that you can plug in that will actually get you to 0, and there's definitely no value of x that you can plug in that will turn this into a negative number. So this gets closer, closer, closer. So what we have is we actually have the x-axis here acts as a horizontal asymptote. And where our graph gets infinitely closer and closer and closer to the x-axis, but it never touches it, nor does it ever cross it. Okay? So our domain for this one would be all real values of x, and our range here is y is greater than 0, not greater than or equal. Well, hold on a second. Greater than 0, because we never can equal 0. Okay? That's what the domain range would look like. Now, your range can change depending on whether or not you've done some vertical shifting. So in other words, if we tacked on a +3 here, all of these values are going to be shifted up 3. So instead of going through 1, 1, it's going to go through 1, 4. 1, 2, 3, 4. You're going to have the same shape, but instead of 0 acting as the asymptote. Your asymptote is now going to be at 3 here. We've shifted instead of a plus 0, we now have a plus 3. So plus 3 is now your 1, 2, 3 is now your horizontal asymptote. And so your function is going to start at infinitely close to that. It's going to cross 1 up from there, and then it'll exponentially grow from there. In which case now our range would be y is greater than 3. Okay? So that's the gist of what's going on with exponential growth. I guess I could do one with exponential growth also where we have a horizontal translation. Vertical translation is like the same thing we learned in chapter 3, I think. Here we're adding 3 outside the function. What does that do? It translates it up 3 units. Vertical translation. Well, what if we had f of x equals, how about a 2 times x minus 3? Okay, well, let's think about that. If I just have y equals x, or 2 to the x, if x is 0, that gives me where I'm 1 up from whatever the horizontal asymptote is. Now, if I have x minus 3, well, what value of x will make my entire exponent 0? Oh, x needs to be 3 in order for my entire exponent to be 0. In other words, when x is 3, this behaves the same thing as when x is 0 here. So what I've done is I've taken my black curve here and I've shifted it to the right 3 units. So I've horizontally translated 3 units to the right. So that would make it, so rather than going through 0, 1, it's going to go through the point 1, 2, 3, 1. And I still have the horizontal asymptote at 0, and I'm going to grow from there. So vertical translations, adding and subtracting up, down. Horizontal translations, subtracting and adding right, left. Just like you've had with other kinds of functions, we have the same thing happening with our exponential functions. So that's growth. Okay. What would give us decay? Well, that would be if 0 is less than b is less than 1. That would be something like if we had f of x equals, let's just say we have, oh wait, I don't need parentheses there, sorry. We had like 1/3, no, I do want parentheses there, to the x, because it makes it clear it's not 1 to the x over 3, it's 1/3 to the x. Well, what happens now is as our x values get bigger, we're going to start at 0, 1. As our x values get bigger, oops, I'm going to go from 1. 1/3 to the first is 1/3. 1/3 squared is 1/9. 1/3 cubed is 1/27. And then when we rewind, if x is -1, 1/3 to the -1 is the same thing as flipping the fraction upside down to the +1, so that gives us 3. X is -2, we have 1/3 to the -2, that's the same thing as 3 to the +2, which is 9. And so as we go backwards, we're exponentially going up, and as we go forward, we're getting closer and closer and closer to our horizontal asymptote. So that's going to look like this. If x is 0, we're still crossing there at 1, but now we start big and we level off, and we level off closer and closer to that horizontal asymptote. So this would be exponential decay. We still have a domain of all real values of x. We can plug any number in for x and solve. We still have a range of all y values above my horizontal asymptote. In this case, the horizontal asymptote is 0. So I have all y values greater than 0. If we had like a +5, that would shift it up 5 units. Then my horizontal asymptote would be at 5, and I would have all y values greater than 5. Okay? So that's that. Now, practical application, we have a lot of stuff where growth or decay happens exponentially. So it might be something like you have a bacterial population. or viral population to make it really on topic with the news. So it might be something like if on average one virus infects a cell, forces the cell to make more viruses, and then 100 viruses release. Each of those 100 viruses infects a cell, then makes the cell make and release 100 more, and then each of those becomes 100 more. So you have exponential growth where one becomes 100, each of those 100 become 100, each of those 100 become 100, and you have exponential growth. Or if you have some medication that is killing things off, then you would have like exponential decay happening like that, the opposite of growth. So we have a couple equations that we can use for growth and decay. And one of them, we have n, let's see, let me go ahead and give some label for this. This is exponential growth or decay equation. We have n equals n naught, or n sub 0, times 1 plus r to the t, where n is final number, or final quantity, maybe I'll say quantity. N sub 0 is initial quantity. R is rate of growth as a decimal. In other words, if you have 20% growth rate, R would be 0.2. And then T is time frame that growth rate is based on. In other words, if your growth rate is, this population is growing at 20% per day, and you want to know what the population will be in 1 week, well, the rate is based on number of days. So if you want to know what the population will be in 1 week, you have to say T is 7 days. If you have something like, oh, this population is growing at a rate of 20% per year, and you want to know what's the population going to be in 5 years, well, you would use 5 for T, because your rate is based on years and you are using a T value based on years. So the time frame that the rate is based on and that the T is based on, they have to match each other. So either you have to adjust the rate or adjust the T value, and I think it's a lot easier to adjust the T value. If you have exponential decay, then you have a negative R value making this minus. So let's say you have 20% decay, this would become 1 minus 0.2, which would give you a 0.8 here, which then gives you this scenario here where you have exponential decay. Okay? All right, so you'll have a couple of problems to do that are along that line. Let's maybe do one sample problem real quick. So let's say we have a population of kangaroos. Kangaroos is decaying at a rate of, let's go 15% per year. If the initial population is, let's go with 32,100, find the population in 3 decades. All right, we'll go with that. All right, well, let's plug in what we know to our formula. N equals n sub 0 times 1 plus r to the t. All right, I'm trying to find n, right? Find the final population. Okay, that's what I'm looking for. Initial population I was given, that's 32,100. Okay, times 1. We have, now notice this is given as a positive rate, but I'm told it's decaying. So I need to make that a minus 0.15. Okay, and then 3 decades, well, my rate is based on per year. So I have to say that t then is 30, because 3 decades would be 30 years. Now I can go from there, and this is just a plug and chug on your calculator kind of thing. So we have, I oftentimes like to do this first. I like to do my 1 minus 0.15 equals, okay, now I have that value. I'm going to raise that to the power of 30, to the 30th power equals, that gives me this value, then I'm going to multiply it, 32,100, and I get 2244.9. Now what are we dealing with here? We're dealing with a population of kangaroos that is dying off. Okay? So I'm going from bigger numbers to smaller numbers. Now, because I'm dealing with kangaroos, 0.9 doesn't make much sense. All right? So what I would do is I would round. Now the question can be, do you round up or do you round down? Now in this case, I'm at a bigger number and I'm decreasing, right? I started big, I'm decreasing over time. So I just finished being at 245 kangaroos and I am decreasing more, but enough time hasn't gone to decrease down to 244 yet. So I would say my answer here is 245 kangaroos. I'm not rounding up to 245 because 0.9 rounds up. I'm rounding up to 245 because that was the last whole number of kangaroos that I had, and I haven't decayed down to the next whole number yet. If this were growth and I was increasing, and let's just say I started at 12 kangaroos and I'm increasing here, I would round down because the last whole number of kangaroos that I had was 244, and I haven't quite reached the 245th yet. That's how I would do the rounding here. All right, hopefully that makes sense. And then one other formula that we have is a particular application of exponential growth, that is compound interest. Compound interest. Compound interest, very similar to exponential growth, except rather than us like kangaroos, we're just assuming that new kangaroos are being born whenever they happen to be born, and that there are not specific intervals at which the growth happens. Compound interest, there are specific intervals at which the interest is applied, or specific intervals at which the growth happens. And so the formula ends up being just a little bit different. And here's what we have. We have A equals P times 1 plus R over N to the NT, where A is final amount, P is, I could say initial principal, R is annual rate, N is number of compounding periods per year, and T is number of years. Okay? All right. So what happens is the R over N. So let's just say it's 8% interest, compounded monthly. Okay? So you'd have
0.08, right? 8% would be 0.08. This is compounded monthly. What that means is each month you're getting 0.08 over 12 is the amount of interest that you get. And then n times t gives you the total number of time periods that where the compounding has happened. So if you're at 10 years and it's compounded monthly, well, what does this exponent become? 12, because compounded monthly, times 10 gives you 120. In other words, this gives you the number of months that is where the compounding has happened. And then the annual rate over 12 gives you gives you the monthly rate. So this goes from annual to now monthly, and then this n times t gives you the number of months. So the formula is kind of doing a little bit of the work for you of making sure that the number of compounding periods is matching the rate, the time frame that the rate is based on. Okay? Let's do an example. Let's just say you get a job and you get $1,000. Let's say you deposit $1,000 into a Roth IRA. And it earns, that'll work, 8% annual interest. Well, Roth IRAs won't really be compounded. Roth IRAs, the gist of what it is, it's a individual retirement account. It's a savings account for retirement where you pay whatever your income tax rate is at the time you deposit it, which, like, if you're a student with a side job, your income tax rate is going to be very low. So you pay a very low income tax rate, and then you don't have to pay taxes on it the rest of the time it's there. So it can just sit and grow and grow and grow. And if you have an emergency later on in life and you need to pull some funds out of it, you can pull some funds out of it without getting deducted, without getting dinged with like fees and stuff like that. And you can pull it out without having to pay tax on it because it was taxed at the time that you put it in. But rather than a Roth IRA, because those don't like get compound interest, so I'm just going to say it's like into an account, whatever kind of account it is. And it earns 8% annual interest compounded monthly. How much will be in the account when you are 70 years old? All right, let's see what we're going to. So here's our equation. We're looking for the final amount, A. The initial principal, we're depositing $1,000. And we have this is growth, so I'm going to say plus. 8% is the annual interest, so 0.08 divided by is compounded monthly, so I'm going to go with 12. If it was compounded weekly, this would be over 52. Compounded quarterly, this would be over 4. Compounded, I guess those are the main ones that you're going to run into. Compounded daily over 365, then you get into like, well, wait, but there are leap years in here, and what do I do with that? So I'm not going to deal with that. Times number of years, well, let's see. 18, right? 18, did I say, into an annual account? You deposit into an account, you deposit $1,000 when you're 18 years old. Sorry, I forgot that tidbit. So it sits there, let's just say from your 18th birthday to your 70th birthday. Okay. Well, 20 to 70 would be 50, so this is sitting there for 52 years, compounded monthly. So 12 months times 52 years will give you the total number of months that it compounds. And let's see what we get. All right,
So I personally would do this first, 0.08 over 12. I get that number, and I'm going to add it to 1, so plus 1. Okay. Then I'm going to raise it to this power of 12 times 52. The 52, by the way, has nothing to do with the fact there are 52 weeks in a year. It just has to do with the fact that it's 52 years that it's been sitting there. Okay, that, and I'm going to go times 1,000, and I get this. And what do I have sitting there? I have $63,193.07. That's the amount of money that I have sitting there in that account. Just started at 1,000, deposited $1,000, and it sat there and grew and grew and grew and grew and grew. And then when all is said and done, you have that. If you did this with an actual Roth IRA where it's not like a set interval where it compounds, and if, this is a big if, but if it kept earning what the stock market on average has earned historically, your $1,000 initially invested would turn into somewhere around $250,000 by the time you're 70, I think, maybe 75. But I think 70 is what this was, is what that would turn into. If you just were able to keep adding to that $10 per month, the amount would roughly double, and you'd have about $500,000 of retirement savings just by starting young and then adding even just $10 per month. Yeah, it's crazy how compound interest starts working in your favor more and more and more and more the more time that goes by. Okay, we looked at some graphs, we looked at 2 word problems. I think that does it. Let me know if you have any questions. I'll be happy to help. Well, there's a graph and inequality, the same thing. If it's less than instead of less than or equals, make it dashed. And if it's y is less than, you would shade below. But don't go, well, no, you can have y values. Never mind. This is an asymptote that you can go below. All right, yeah, let me know if you have any questions. Hopefully that'll do it for you. Thanks.